Well, here it is, our last week of Physics 6C. And we've saved some topic now for the last week, which is fairly simple, but extremely important. And today's topic is radioactive decay. Remember where this comes from. If you recall the curve of binding energy for atomic nuclei, we already saw that the most stable combination of neutrons and protons that you can possibly come up with is iron 56. And as you recall, any smaller nuclei than that can be assembled into larger nuclei if you're very clever and you put the right nuclei together to give you a lower energy state. In other words, energy will be released. In other words, by fusing together smaller nuclei up to iron 56, you can generate nuclear fusion energy. However, as soon as you get up to the most stable atomic nucleus, iron 56, then as you start looking at higher nuclei with more protons and neutrons than that, you find the reverse situation. You've passed the maximum stability, and then unfortunately just stuffing in more protons there, of course, is going to make more electrostatic repulsion. It's going to want to blow the nuclei apart with very, very strong forces. So we pack even more neutrons in there to give more strong nuclear attractive force, which can, at least temporarily, overcome the electrostatic repulsion. But there is a limit to how far you can do this, and once you've passed iron 56, no matter how many protons and neutrons you pack in, there is going to be a natural tendency that these more massive nuclei, if they would split into smaller pieces, could reach a lower total energy state. And remember, everything in nature wants to reach a lower total energy state, even me. So atomic nuclei, when they're large, will spontaneously split into smaller pieces because energy can be given off that way in various forms that we'll see. So that's the basic idea of radioactive decay. It's going to happen more and more frequently the bigger the nuclei are above iron 56. Now there are some which are stable above that, quite a few, but as you get past lead, nothing is stable. Everything wants to radioactively decay at some rate. Some of the rates might be very high, some of the rates might be rather low. By the way, radioactive decay could also happen for small, light nuclei that are less than iron 56 if they have the wrong combination of neutrons and protons. So that could be unstable also. So anyway, radioactive decay wants to happen a lot. It's a result of the fission of one nucleus into smaller pieces. And so in today's lecture, I just want to dissect what goes in and what comes out of these nuclear reactions. If you've done chemical reactions, just reset your mind here to what's happening inside the nucleus instead of what's happening to those electrons outside. Electrons outside in the outer parts of this atom are not really going to enter into this game at all. So we're basically looking, I could have called this lecture nuclear accounting. We just have to keep track of what goes in and what comes out, and we have to balance the books, just like a good accountant, a nuclear accountant. I was thinking of calling it this because then we could get a lot of pre-business majors to come and take this course. I wanted to learn more about accounting. Nuclear accounting sounded like the ultimate accounting. Yeah, in some ways it is. And it's not, like I said, too hard to keep track of the main nuclear fission reactions that produce the main kinds of radioactivity, because I'm going to tell you mainly of three of them. There's some others that happen too, but the big three, well, you could say it's the ABCs of radioactivity. This lecture is just the ABCs. Well, actually, this lecture is the alpha, beta, gammas of radioactivity. We're going to start with alpha right here. Let's take a big old nucleus there. Okay, it's not really a green ball, but anyway, it's a packed, very, very dense combination of 88 protons that want to blow each other apart, but held together with their strong nuclear attractive force, which is even stronger, plus the great assistance of 138 neutrons that don't have any electric charge but have the strong nuclear attractive force. Wow, a total of 226 atomic particles in there, or an atomic mass of 226. So how do we know what this nucleus is? Well, the atomic nucleus is identified by the number of protons, which will also determine its chemical properties. 88th element, 88 protons in the atomic table, is Ra. I wonder which one that was. Has a big historical significance to me, and it says useful radioactive element, radium. Remember, first isolated by Madame Curie under heroic conditions of perseverance, probably eventually led to her death from radioactivity after many years, but more importantly, it led to her getting a Nobel Prize for isolating radium, and tremendously, almost heartbreakingly hard work to do it, because there's not a lot of radium in even radioactive ores like pitchblende, so she had to go through tons of it to get a little ounce of it. And as you know, radium glows in the dark from the radiation that it gives off, and when she actually isolated it, she could see it glowing in the dark. Beautiful, dramatic moment in physics there. What is one possibility of how radioactive radium, all these words, similar origins here, what's one possible way it could decay? Well, one possible way it could decay is into radon. Sorry about the confusion of these names here. They both start with Ra. Ra is the atomic element symbol for radium. Rn is what it could decay into, radon gas, which it turns out will also be radioactive. Well, what is radon gas? It's the 86th element in the periodic table because it has 86 protons there, and it has the radon we're talking about here has an atomic weight of 222. So that means the total of the protons plus the neutrons has to add up to 222. So if I just told you that I had radon and it had an atomic mass of 222, and it was 86 protons, you could simply work out by accounting there must be 136 neutrons left over, because 86 plus 136 is equal to 222. I'm sure you can do that arithmetic even on an exam problem. Now, let's do the interesting accounting. Let's look at what all the differences are in the nuclei from radium going to radon. Well, you can immediately see that we have lost 2 protons. We went from 88 to 86. 2 protons must be accounted for somewhere. All right, so put those on your ledger here, you nuclear accountants. We got 2 protons over here. Also, we've lost at the same time 2 neutrons, because we were up at 138, we're down to 136. Or another way you can see this is that we went from an atomic mass of 226 all the way down to 222. So we lost 4 atomic mass units, 2 of which were protons, and yep, the other 2 had to be neutrons. Most likely way that these 2 protons and 2 neutrons came out, that's a very nice little package. You know what 2 protons and 2 neutrons are. We know it as a stable, very happily stable, very stable little helium nucleus. That's right, it's a second element in the periodic table because it's 2 protons, and stable helium also has 2 neutrons. There's a very nice symmetry and stability about a helium nucleus. I'm talking about helium-4 here. And as I said, forget about the electrons. They're not entering into this. So we just have a bare helium ion here, which has a +2 charge. Before people realized what was coming out of radium when it decayed into radon, it was just called radioactive rays. And the first ones that were discovered, I guess by Madame Curie and other people, and her husband, let's not forget Pierre here, and a lot of other very brave researchers in the early 20th century. They called it alpha radiation. Later it was realized that these are actual particles, call them alpha particles. Now we realize, well, alpha particle, that's just a fancy name for a bare helium nucleus, which is going to go tearing off. Of course, pretty soon, since it has 2+ charges, it's probably going to acquire 2 electrons in short order, become neutral helium. But anyway, it exits the nucleus without the electrons. It exits as a bare alpha particle, a bare helium nucleus consisting of 2 protons and 2 neutrons. And now the books are balanced. We lost 2 protons and 2 neutrons, but the decay product, radon, which is called a daughter of radium, also gives off at the same time in opposite directions here, so that the momentum will be conserved. A helium particle, helium nucleus, will fly off in the other direction. So that's pretty much what all alpha decay processes are going to look like. Now, what about this alpha particle? By the way, the radon particle is still radioactive. Radon gas, you know, is definitely radioactive, so it's probably going to fission further, giving off more radioactive decay products. But then we'll see what that is in a few minutes, but let's not worry about the moment. What about this helium nucleus here, this alpha particle? Well, that is going off probably at a pretty high speed with a lot of energy, but like I said, it has 2 plus charges here, and so it's going to slow down pretty quickly when it interacts with any other matter. It's going to start acquiring electrons and so on. So it doesn't actually have to go through very much matter. It'll maybe go through the air. That's such a thin amount of atoms in it. But as soon as it hits anything, just in the least bit solid, it has a very good chance that it will have interactions and it will eventually be absorbed until it becomes something harmless. So, to take an example, I'll show you in class, if I had a sheet of paper, just one sheet of paper, probably enough to stop most alpha particles that result from radioactive decays. Or, that's a more interesting one, suppose you don't walk around with paper in front of you. Suppose you're exposed to a big burst of alpha particles. Most of them will be absorbed in the upper layers of your epidermis. Ooh, wow, I used a biology term there. Good on me. And I have read and sort of confirmed experimentally here that the epidermis, the top layers of your skin, are dead. So I don't really care how much, really too much radiation being absorbed there. I don't think that's going to be a really profound impact on my biology. However, what if the alpha particles, this is radioactivity after all, what if that were to get at my living cells without anything in the way? Well, that can happen in 2 ways, of course. First of all, I could breathe it in from the air into my lungs, and there's no epidermis, there's no dead layer protecting my delicate lung cells from absorbing this radiation. Or I could, and this would be not really too smart, I could drink it or eat it, and then it comes right into my intestines and so on, and then the radiation is quite damaging, because that's a fairly massive particle compared to other radioactive particles. So when it bounces around in a living cell, it has a lot of energy to deposit. It will mess up quite a number of molecules in there. It doesn't take much energy to break them apart and reorganize them. And one of those molecules, for example, might be a DNA molecule that you didn't want it to be messed around. You didn't want to have a mutation, for example. And there are other things that can just generally break down the physiology that was working fine before the alpha particles got into your cells. So that's kind of the paradox of alpha radiation. Fairly easy to protect yourself against, like don't eat it. But very hard. If you don't protect from it, it's probably the most damaging radioactivity that your body would have to deal with. All right, here's the next radiation that was discovered, I guess, historically, beta radiation. Well, we know now that beta particles are actually individual electrons. They should have just called them electrons, but that the history of this and the naming scheme was before the Curies and other people even realized what the radiation was that was being emitted by their different radioactive samples. So one thing that some kind of radioactive samples can give you off is very high energy. I have to stress this. These electrons come screaming out with an enormous amount of energy, way more energy than any kind of electrons we find normally cruising around here. Actually, it turns out that there are 2 kinds of beta radiation. One is negatively charged beta particles, which are electrons, and we'll actually call those beta minus, if you want to keep track of this. And another possible decay product is positrons. That's interesting. we haven't really seen positrons in this course before. It's a form of antimatter. And the reason we don't see positrons much around these days is because antimatter has a very short lifetime around here in a world of matter. Because as you realize, a split second later, any kind of positron, positively charged electron, just like an electron in every detail, mass, same amount of electric charge, except it's a plus instead of a minus, the antimatter will find its matter counterpart and they will annihilate, producing a pair of gamma rays almost immediately. This is a matter world. Virtually all of the antimatter was destroyed early on in the Big Bang. Thank goodness there was a little bit of matter left over. That's what made us, that's what made the universe. Well, these little high-energy electrons are a lot harder to stop than a big, heavy, lumbering alpha particle. Think about this. This thing is several thousand, maybe 10,000 times less massive, and it has a great deal of penetrating power. And so that's not good. Much more difficult to shield against beta radiation. The good news is that a single high-energy electron let loose in a cell in your body won't do nearly as much damage as a single alpha particle, but still, I'd rather it didn't get in there. How do these beta particles get produced? Either an electron or a positron? Well, it's all about keeping the books balanced here. Actually, it's about a nuclear transformation in the atom. I'll show you one right here. Basically, whenever neutrons and protons are going back and forth between each other. Oh my gosh, where did that come from? I mean, I know neutrons and protons have a very similar mass. They're rather similar particles, but this is the first time I think we've realized in this course that a neutron can actually change. It can metamorphosize. It can morph into a proton. Wow, that seems like that would violate all kinds of accounting books, doesn't it? Let's see. First of all, could energy be conserved here in this reaction? Well, yeah, because a neutron has ever so slightly more mass than a proton. All right, so that means that mc squared of a neutron, m sub n, c squared, is a bit more than m sub p, c squared. So yes, there is extra energy available. We won't be violating the conservation of mass energy here by this reaction. What about electric charge, though? Wait a minute. Here we have 0 net charge. It's a neutron, that's what it means. Now we have a proton here with a plus charge. The only way we can balance the books, which we must positively balance the books on total electric charge starting out at 0, is to make a minus charge. To make a minus charge out of nothing. That's right. So in this neutron decay here, a proton results from the neutron with the creation of a brand new electron. So we balance the books with one minus charge and one electric plus charge. Still 0 charge in, 0 charge out. And there's a great deal of energy that comes off with this. A lot of it will be carried away by that electron, which we'll call a beta minus particle. Still, it turned out that some additional energy and some additional momentum, not only additional electric charge, but additional energy and momentum was required to make this reaction happen. People were aware of this for quite some time, I guess in the 30s and 40s, studying this, and it was really, this is one of science's greatest hits, actually. I'm very impressed by the people who did this. They postulated that there must be a new particle that has 0 electric charge and has very little interaction with any other matter, but it can carry energy and momentum. In fact, it could be virtually massless particle, and pretty good name for this. It's a very little thing, little dinky thing, but it was required to exist if this equation was going to balance. It's called, they postulated the existence of a neutrino. Took decades actually to experimentally confirm that neutrinos do exist, and they are produced in this so-called beta decay process. In fact, neutrinos tend to get produced by any process in which protons and neutrons go back and forth between each other, because this can only happen due to the weak nuclear force. And a neutrino is a particle that only experiences the weak nuclear force and gravity. it does not experience the strong nuclear force. So this example of beta decay, the production of beta plus and beta minus radiation, would be a very excellent example, wonderful example of a purely weak nuclear reaction which only can come about because of the weak nuclear force. Now let's see what the results of this are. It says right here. We've actually given up a neutron here. Now this is very counterintuitive, and so you really got to get your mind around this, or you'll probably mess up. You've probably been thinking so far, based on alpha radiation, alpha decays, that the heavy element, the heavy radioactive atom nucleus, is continually marching down the periodic table to smaller numbers of protons, to lower number on the atomic table. But this beta decay reaction does the opposite. It moves the decaying nucleus back up one step in the periodic table, because it previously had a neutron. Now it finds that it has an extra proton. That's right. So it's gone one step up in the atomic periodic table. By the way, there's also another possible reaction that could happen. This is less likely, but this is going to require some more energy here. But you could have a proton decay into a neutron in order to balance the books on the electric charges. We have to have a plus charge here. So that's what my E plus here means. E plus is what I'm calling a positron. Right? It's just like an electron. That's why I put the E there. So much like an electron, except it's got a +1 instead of a -1 charge. Same mass as the electron. All other properties the same. It's a little form of antimatter, and it isn't going to last very long. It's going to annihilate within the first electron it finds and make 2 high-energy gamma rays. How high energy? Well, the entire rest mass, what is it, a bit more than 1 MeV, 1 million electron volts here. The entire rest mass of the electron and the positron is going to get converted into the energy of 2 MeV gamma rays, which themselves, by the way, could do a lot of biological damage. All right, so now we've come up with beta radiation. That leads in, or segues in very naturally, to radiation from gamma rays. Oh, finally I get it. I was always wondering, you know, in the table of the electromagnetic spectrum, of going to higher frequencies, we got to ultraviolet, we got to the X-rays. I guess that was named when nobody knew that they were just a high-frequency form of electromagnetic radiation. Well, the early radioactivity explorers also didn't realize that gamma radiation was actually just an even higher frequency electromagnetic radiation with frequencies above the X-rays. They just saw this very high energy radiation coming out and causing various amounts of mayhem here. What they'd actually discovered was that in radioactive decays, there are a number of ways that very high energy photons, which for historical reasons we still call them gamma rays, gamma radiation, remember alpha, beta, gamma, get produced. Let's look at one example here, going back to our earlier decay of a radium nucleus. There's a radium nucleus. It's 226 total atomic mass units, 88 protons, and as we saw before, it has a chance that it can emit an alpha particle. There's the alpha going away, and it can end up being radon. But there actually are 2 possible forms of radon that the radium can, with various probabilities that are dictated just by probabilities of quantum mechanics, various probabilities that will take this path to go down to the lowest energy form of radon, or, this is another path that can definitely happen, it can end up in a so-called excited state of radon here. Now this is not like the excited states that we've seen before, where we're just dealing with small energy differences because we're talking about the outermost electron. That was all of chemistry. Yeah, chemistry involves some small excitations of the outermost electron. I'm talking about the innermost electrons. Remember, the innermost electrons are so close to this nucleus that they are bound by much, much stronger electric attraction forces. So the potential, the electric potential energy of an inner electron is huge, thousands of times more than those outer electrons. And so if it's an excited state, it probably on very short order wants to decay down just like in chemistry, the electron wants to decay down, except this is an inner high-energy electron, wants to decay down to the ground state. And that's a long way down. In this particular example, it's, wow, look at this, 186,000 electron volts down to the ground here. And just like we saw before in chemistry, in our quantum mechanics stuff, when you drop down from a higher energy level to a lower energy level, the energy has to balance the books. A photon is created, but in this case it's 186,000 electron volts, or 0.186 MeV, 0.186 million electron volts. Photon created out of nothing, not out of nothing, out of the energy the electron gave up here, and that goes screaming out at the speed of light as a high energy gamma ray, and look out if it comes your way. These, they don't have any mass, they don't have any electric charge, these gamma rays. Very difficult to stop them. In fact, I'd say probably gamma rays of, I don't know what has caused more paranoia and fear and, justifiable concern, probably of all radiation. I'm worried about radiation, man. I want you to know what you're worried about and what the specific properties are. Gamma rays are a worry because you have a very difficult time shielding them out. It takes a big shield. In particular, air is certainly not enough. I don't care how many layers of paper you have, it's not enough. You really need big solid walls to block them out. Lead is nice because it has a very high density of particles, so you could have, a lead shield. That would be pretty good. Nobody, frankly, wants to walk around in a lead shield. Basically, this was what the purpose of a fallout shelter was. You need, I don't know, many feet or meters of dirt or concrete in your way between the gamma rays and what you're trying to protect, your body, your loved ones, whatever. So this is the main reason that it was popular to build fallout shelters, when we thought there's some possible justification that those crazy Soviets might nuke some of our cities. Thank goodness we don't have to have fallout shelters now, but that's what they have to do. They have to have enough solid material, like I said, like meters of material, or dirt, concrete, lead, whatever, to block out these highly penetrating gamma rays. The, quote, good news, if there is any good news about gamma ray radiation, is that although it's hard to block out, it doesn't do nearly as much damage, not nearly as much as an alpha particle, getting loose in your cells, in your DNA. So still, I wouldn't want any more gamma rays than are necessary. Of course, gamma rays and beta rays and even alpha rays are coming into our bodies at all times simply from outer space. Although our atmosphere does a fairly good job of protecting us from most of them, particularly gamma ray radiation is coming from outer space. It's produced in our upper atmosphere. By the way, if you're an airline pilot or you're a frequent flyer, there's less atmosphere up there, and so you get exposed to higher levels of natural background radiation. If you live in Denver, you're exposed to higher levels of background radiation than here at sea level in Los Angeles. And fortunately, these are fairly small amounts generally, and so we can live with it. But I certainly don't want to have a lot more of it, such as what gets produced in a big nuclear explosion, say a fission bomb, for example, which we'll talk about in a minute. So here's our little summary of RBE. Wow, there's a fancy term I didn't know before, relative biological effectiveness. I don't know exactly how they figured this out. I guess it depends on what we're talking about, but I'm thinking about, destroying key molecules in your cells, such as DNA, or changing them. So if we normalize everything to the damage caused by gamma rays, that's one. Well, beta rays getting hit by the same amount of radiation of beta rays is fairly similar. Alpha particles 20 times worse. That's why I really don't want these running around inside my living cells. Now, there's a few other things that I haven't mentioned here that could be radiation that could get produced and exposed to us as a result of radioactive decays. Heavy ions. We could occasionally have larger nuclei that have more protons, and I don't know what they could be, cesium, iodine, whatever. And they're also like this alpha fallout. They are massive particles. They don't go very far. They're fairly easy to block, but you really do not want to be ingesting them. Very bad. Bare protons will occasionally come out. I haven't shown you any reactions to that. I don't think I'm going to ask you reactions. The reactions I'm going to ask you on the exam are alpha decay, beta decay, gamma decay. That's the only ones I've ever seen on the MCAT. Some of these other ones could happen. Protons are sort of intermediate. They have a lot more mass than electrons and positrons, so they're more damaging. Here's another interesting one on the table here. Neutrons. I hadn't thought about that one before. A neutron could be produced and released, a free neutron. I don't usually see free neutrons. They're usually locked up in atomic nuclei. But what if a free neutron were to go out into the environment? The bad thing about neutrons is very easy for them to get into an atomic nucleus in your body because there's no electric repulsion force that's trying to keep them away. Protons will be opposed by the plus charge of all nuclei. But neutrons go right in there instantly. Oops. Then they have produced what? A neutron has been absorbed. It's produced a new isotope of whatever the original nucleus was in your body. But as you know, a new isotope, because it has an extra neutron that wasn't originally wanted there, has a very good chance of having turned it into something which is now radioactively unstable. And that's very important. So that's the main thing I do not like about neutrons here. Sorry to be giving my personal opinions on this. Problem with neutrons is that they will be almost immediately absorbed by all the normal nuclei, for example, and it could be in your body, and they will cause them now probably to be radioactively unstable, new isotopes that you did not want in your body. Or they could have other constants too. We'll see in a second. Let's look at more real, well, I'm going to go back and look at the decay of radium into radon. We'll see that that actually is part of a chain. Like I said before, this is a little complicated. It's worth thinking about for a few minutes here. Most radioactive elements start out with very large numbers of protons and even larger numbers of neutrons. Remember, the most stable atomic nuclei as we go to very large nuclei will have quite a bunch of extra neutrons there to give us a little bit more strong nuclear force to hold them together. But still, they are radioactively unstable. So they want to go, let's look at this diagram. Here we have on the horizontal x-axis, we have the number in the periodic table, the atomic number. In other words, the number of protons on the x-axis here. Let's see, lead, 82, pretty special one there, because anything that has more protons than 82 wants to at some point break apart in a fission reaction, some kind of radioactive decay, polonium, radon, radium, what is that, francium, actinium, thorium, etc. All right, and uranium here. And then even above uranium, neptunium, they were in a sort of a planet mood, the years when they were discovering those. Let's look at the most common nucleus, the most common isotope of uranium. Wow. This is worth knowing, actually, because uranium was our first really big success in fission when we were able to isolate that from uranium ore. That's what the Curies were messing around with, for example. It has 238 total mass particles. Let's see. Since it has 92 of those are protons, that's how I know it's uranium. By subtraction, 92 from 238 leaves me, correct, the number of protons on the vertical axis here, and the number of neutrons. That's a slap, sorry. And the number of neutrons, that's a good name for it, must be 146. So we have 146 neutrons here trying the best they can to hold together these 92 protons from exploding. And I have to say, they do a pretty good job of that, because it will stay stable on average, statistically, for a pretty long time. But which way is it going to decay? The most likely decay for any kind of large radioactive nucleus is it wants to stay fairly close to the line of maximal nuclear stability. Now, we remember that the line of maximal nuclear stability for very small atoms usually is equal number of protons and equal number of neutrons, such as carbon, such as helium, such as oxygen. They like to have matched numbers of neutrons and protons. But as we get to very, very massive nuclei, we found we had to add more neutrons in. So what that means, what I've just told you, is that the line of most stable nuclei will gradually veer up to a region where there are a lot more neutrons compared to protons. And you see how far it's gotten away from protons equals neutrons. By the time of uranium, geez, we've got like 50% more neutrons than protons here. So generally, you're expecting radioactive decays to want to give up neutrons on protons, but there should be a bit of a preference for giving up neutrons to stay close to stable nuclei. So the first thing that a uranium nucleus will do is it will give off 2 protons and 2 neutrons, and that's your pretty standard thing. It gives off an alpha particle and it decays to thorium-234. Is that arithmetic working out there? How's the nuclear counting? We gave up 4 atomic mass particles, 2 of which were neutrons, 2 of which were protons, so we jumped. We skipped down from periodic element table of elements 92 all the way down to thorium number 90 here, and it's 234 instead of 238. Actually, that takes a long time to happen on average. As soon as you get to 234, thorium says, gosh, I'm feeling really, I have 2 less protons and 2 less neutrons, but I'm feeling really overloaded with neutrons. And so what does thorium do? Aha! It changes one of those unwanted neutrons to a proton. Ta-da! Very simple little one-step process here. And it has gained 1 proton, so it actually went back up to atomic element 91. And it has dropped 1 neutron, so it's just exchanged 1 neutron for 1 proton. So it's gained a +1 electric charge here. What's happened? Beta minus decay, the little blue line here. 1 electron, 1 minus charged particle had to be emitted entirely. It goes out of the nucleus. Electron's not going to stay in the nucleus. It's gone off with its high energy to find new things to do, new trouble to get into before it runs into, well, a lot of new trouble before it gives up all of its energy. And then, a very short time later, this element wants to be added again, another beta minus decay, causing another neutron to be turned into a proton. So wow, it's back up to uranium again. What are we accomplishing in this? Gosh. We've had 3 decays now. 2 protons were eliminated from the system with an alpha particle. Then 2 protons got created in the middle. But we have lost 2, 3, we've lost 4 neutrons. So it's a different kind of uranium. It's now a very unstable isotope of uranium, uranium-234. That is going to go on a rampage of alpha decays now. It really wants to get rid of both neutrons and protons at a roughly equal rate, so it just does it 1 alpha after another alpha after another alpha. Jump 2 down in protons, 2 down in neutrons. To thorium, except now, look, it's a lower mass isotope of thorium, only thorium-230. Only has 140 neutrons and 90 protons, and it wants to do it again. Gets down to radon, that's 138 neutrons and 88 protons. That's the radon, sorry, the radium. Did I say radon? That's the radium. God, even I made that mistake. That's Madame Curie's radium. And as we saw earlier, that wants to decay by another alpha decay, classic alpha decay, to 222 radon. And radon doesn't stop there. After a very short time, 3.8 days, it's got a 50-50 chance of decaying into polonium. It's nice. I think that was named after Curie's home country there. And then it'll decay again down to lead. Whew. Are we finished there? We finally got into something stable? I'm sorry, that is not the most stable kind of lead. It's got too many neutrons in it. Stable lead wants to have an atomic mass of 206, it wants to have only 124 neutrons on it. 214 lead, not at all stable. So it's got too many neutrons in it, so it beta decays into bismuth. And now we have an interesting thing. You don't need to know, by the way, any of these steps. I'm just giving this to you as an illustration of the different things that happen in a radioactive decay chain. It's a series. It's not just one example. And many of the problems will just isolate one example, radium to radon. But you got to be aware this is a whole chain, a cascade that's going down. And at this point, when we get to 214 bismuth, which is radioactively unstable, it wants to fission. It has two possible ways it can go. It can alpha decay, what is that, thallium, or it can beta decay back up to polonium. Either way, and then this is going to beta decay again, and this is going to alpha decay. Either way, you end up at lead 210. Either way, still not stable. So after a few decades, that'll decay to a smaller nucleus of bismuth, then it decays, beta decays. Finally, from polonium, half-life 138 days, we decay down, finally, to stable lead. Whew. Okay, so it's a combination of alpha decays and beta minus decays. That's your most common way of getting from an unstable, very high mass, neutron-rich nucleus all the way down to a stable atomic nucleus, lead, and it'll stay there forever. That's nice. That's one of the reasons why there's a little more lead around than you might have expected otherwise, because many other radioactive elements above it ended up decaying to that. Now, as I already mentioned here, the actual amount of time that these radioactive decays take cannot be predicted exactly. That's one of the mysteries of quantum mechanics. We can only state a probability. We can calculate that pretty accurately, or we can experimentally measure it in a laboratory if you have a fair amount of patience or you have very rapid measuring equipment in some cases. And the way we want to measure this typically is we want to say how long, for example, does uranium-238 have to sit around? Suppose they have a large quantity of it, trillions of nuclei of uranium-238. How long do I have to wait? How much time must pass until half of it has decayed? Until there was a 50? I can't tell you which ones exactly. That's the fundamental indeterminacy of quantum mechanics. But I can say statistically, on average, half of them will decay. Wow, it's a long time. It's just about almost the age of the Earth. Interesting. And the age of the Moon. 4.5 billion years. So it's almost stable, actually. But if you wait long enough, it will decay. Or if you have a large enough quantity of uranium-238, and if you have trillions of them, some of them are going to decay in the next minute. A few of them. And they'll keep on decaying gradually, and after 4.5 billion years, I'll have half of it left. And after 9 billion years, I'll have a quarter of it left, and so on. And after 13.5 billion years, only an eighth of the original still survives as uranium. The rest of it has probably gone all the way down to lead. The next steps go fairly fast. Half-life of 24 days for that beta decay, 70 seconds for that one. You better be on your toes. Some of these first radioactive decay rates were like just a matter of minutes. And Enrico Fermi and his friends and assistants in Italy were literally running around with the samples, taking them in the lab so they could measure them before they decayed. Very exciting real-time stuff. And then it got down to uranium, where there was a bit of a snooze, a pause, where I actually had to wait a few 100,000 years. And then to decay from thorium, 75,000 years. Then the radium decay, only a half-life of 1,600 years. And then radon, boy, that went very fast. In less than 4 days, half of it's decayed. Polonium, what is that? 3 minutes? Ooh, that's a fast one. 27 minutes. Look at this one for polonium here. It's 1/10,000th of a second. It's like almost instant. It's like it almost isn't there. Just like that. Very, very fast. Although, as I mentioned, 1/10,000th of a second is a pretty long time in the life of an atomic nucleus, where even a millionth of a second is a fairly long time. Anyway, eventually, it will wind on down the ladder here, maybe by different paths, and will end up as stable lead. Now, the whole point of radioactive decay, or any kind of decay that's governed by the laws of quantum mechanics here, is we have a probability, and since the probability of any one unstable nucleus, or it could be also an unstable electron that wants to decay, the probability of it decaying is a constant over time. So the number of decays you'll get, this is very important, the number of decays you'll get will be proportional to how many of the unstable nuclei you have initially. And so, classic problem in calculus, which we're not going to solve in this class, is but when the rate of change of a quantity is proportional to minus a constant times the amount of that quantity, that is the formula for an exponential decay, just like discharging a capacitor. The half-life of these radioactive decays is very similar to a concept you saw, hopefully in 6b, of the time constant of like a discharging capacitor. But anyway, it's just the calculus of a process which is proportional to the number of atoms in the process. So as the number of atoms goes down, then there's going to be less decays because there's less waiting around to decay. So it exponentially decays, and you can measure that by the characteristic time constant, the half-life. All right, one thing I've left out, but it's so interesting I have to mention this here because people need to know about this. Some kind of decays can happen when a neutron enters a nucleus. I already made some dark comments about this earlier. I said a neutron can very easily get into a nucleus, nothing stopping it. There's no electric repulsion at all because it has no charge. And as soon as it gets into that nucleus, it will change that nucleus. It's made it one heavier isotope. It's still the same atomic element. For example, in this case, it's still uranium. But suppose it started out as uranium-235. A very interesting isotope of uranium. Uranium-235. Not the normal one. Not 238, but 235. I'm going to be specific here. It bumped it up temporarily to I guess, to 236. Uh-oh. There is no uranium-236. It's not stable at all. The absorption of this one little neutron here has unstabilized, what is the word, destabilized uranium. I mean, it was thinking about radioactive decaying anyway. Eventually, maybe it takes years or thousands of years. But just that moment the neutron comes in, it's going to want to immediately decay. Number of different ways it could decay. Let's look at one common one. It could break up into two big pieces. This big piece here is the 36th element, very nice stable thing, krypton gas. So one krypton nucleus goes off, and there's a fairly stable one here. 56th element, barium. So look what's happened here. We had 92 protons. Is the nuclear accounting still going okay here, folks? Sure it is. 92 goes to 36 plus 56. All protons accounted for, no problem there here. These two little pieces go flying off, and they won't be heard from again, probably. Okay, oops, I'm sorry. We better check out those neutrons. I want to check out those neutrons here. We had one here, let's see, so we had 236 minus 92. What is that? 144. We had 144 neutrons. Well, you can add up the number of neutrons in this and the number of neutrons in this, and you'll find immediately that they only account for 141 neutrons. Well, you guys are good nuclear accountants by now. You know, I'm sure if you're auditing a company and they've misplaced, you know, $3 million, you want to keep track of that. Well, I definitely want to keep track. Where do those 3 missing neutrons go? They just went back out into the environment. So one neutron, this is what's so interesting about this. One free neutron, it's unusual to have them, but one free neutron comes in, 3 neutrons go out. That's part of the products of this more complicated radioactive decay. This was an induced or stimulated radioactive decay that got caused by the absorption of a neutron. So we have 3 neutrons coming out here, and now here's where things get possibly interesting. Some of those neutrons, under the right conditions, could possibly be absorbed again in a second generation by uranium nuclei. In particular, what if, just go with me here, what if, I don't know, one of the neutrons gets lost here, don't care about it, But 2 out of 3 of the neutrons find their way rapidly. They're traveling at high speed. They find their way rapidly into 235s. What's going to happen? More or less the same thing as before. These are instantly destabilized. You can't have uranium-236. They instantly decay by fission. Oh, I just showed a few others to illustrate here. Could break up into cesium and rubidium, or this one could break up into strontium and xenon. There's a number of different ways that, oh, now actually we're getting some heavy isotopes here, things like strontium-90, which themselves could be radioactive, and as we saw earlier on our RBE table, could themselves be harmful to like living cells and could be a form of radioactive fallout. That was not particularly welcome there, but that's not the main thing I'm interested in here. If you add up the products here, you will find, once again, they have 1 or 2 fewer neutrons than the original combination here of 144 neutrons that we had at the beginning of this. This is a second generation process here. And wow, so free neutrons get released again out into the environment, and some of them may once again encounter a uranium-235. Here, a lot of them encountered uranium-235. I think this thing has been set up to have a lot of uranium-235 around. Must be a pretty high density of the stuff for this to really get going. And then what happens? We could have, for example, this krypton barium fission, that's just the same one that I started with here, releases 3 neutrons. This cesium rubidium one releases 2 neutrons. Some of these release 2 or 3 neutrons. See what's happening? Every new we have one radioactive decay here, that's the first generation, and it gives off more neutrons than we started with, and they're free, and they're looking around to cause trouble. They're looking, very likely, to stimulate more, further, spontaneous nuclear reactions, nuclear fissions that wouldn't have happened otherwise. These uranium-235s were more or less minding their own business until a shower of neutrons started invading them. And you can add this up. There's all these different probabilities, or you can measure it, but it looks like the yield of neutrons here is like between 2 and 3 times the original neutrons coming in. In other words, we have a neutron multiplier going on here. Every 1 neutron that comes in produces 2 or 3 neutrons in the next generation, each one of which, or many of which, will cause yet more radioactive decays. They'll stimulate more of these radioactive fissions until we get a cascade. A chain reaction has occurred. This is a chain reaction, and a chain reaction is exactly what makes uranium-235 so very fissionable. All you have to do is put 1 little neutron in there if you have a high enough density of uranium-235. Uranium-238 doesn't really have this property. I don't think it produces much more than 1 free neutron out for a free neutron going in. I don't know what the yield is, but it's much, much less. Uranium-235, very rare. Basically, it was the first atomic element that humans could separate. Quite difficult to separate it from the other isotopes at 238. In fact, everybody thought it was impossible until we invented the Manhattan Project. We came up with 2 different ways to separate the heavier 238, which we didn't want, from the 235, which is much rarer, so we could purify the 235 into a quantity that could sustain a chain reaction here. That's, if it's a really fast chain reaction, then we've got an atomic bomb here, a fission bomb. And of course, to make them work, we need to have a relatively high purity of uranium-235, and then we have to bring it together. Oh, that's the other thing. We have to bring it together in a very high dense state. Actually, you have to crush it. You have to implode it because it's not normally dense enough. Too many of the neutrons would just miss. They go, "Oop, I'm out of here. I'm out of the bomb." But if we crush it down with explosives, for example, we get a critical mass of uranium-235, which will eventually lead to so many neutrons getting produced that they will all cause fissions, and they will all, everything will decay in a matter of much, much less than 1/1,000,000th of a second. That's an atomic bomb. That's how we won World War II and pretty much more or less kept the peace for another 50 years with other enemies. And I'm thinking of the Soviets here, not to name any names here. Not the Russians. The Russians are our friends, just the Soviets. But on the other hand, it's also the source of great potential power, heat, for example. And that doesn't produce, greenhouse gases and all of that bad stuff. Really doesn't produce smoke and particles and anything. It just produces some radioactive, small quantity of leftover stuff. But, of course, you do have to keep this reaction controlled. You don't want too much heat to build up or you get an explosion, which I'm sorry to say happened in the Fukushima Daiichi reactor number 3 here. There it is on a nice morning a few minutes before the tsunami flooded the power supply to the pumps, which was supposed to be protected. We thought they'd be protected against a unprecedented tidal wave, but the tidal wave went over the wall, which is a pretty high wall, and then when we could no longer cool this off, the building went away. It's exploded here and spewed out a lot of radioactive stuff, which, thank goodness, mostly was blown over into the ocean. There's, of course, no substitute for talking about a chain reaction. You've got to see it to actually understand it. If you're willing to go to a lot of trouble and set up a whole lot of mouse traps with ping pong balls on them, you have a pretty good physical analogy to the free neutrons that happen in, for example, a fissionable uranium-235. How's it an analogy? Well, you drop one ping pong ball, and each ping pong ball is a neutron, and when it hits a mousetrap, that's like going inside the nucleus of a uranium-235. The mousetrap is the 235, and it has locked in it another neutron, that's another ping pong ball, which could be liberated by the instability caused by the first neutron coming in. And then you have two ping pong balls coming out. The first one, just to keep track of it, is red, but then there's a red one and a white one coming out. Of course, neutrons don't have colors, and so now you have two ping pong balls, which are both, quite possibly in this demo, going to find two more mousetraps. Two more fissionable uranium-235s to destabilize and cause them to emit two more. So then there'll be 4 ping pong balls in the air looking for more mousetraps. And then the next generation, there'll be 8 of them, then 16, then 32, and pretty soon, very rapidly, just as fast as they can find the next mousetraps, all of those mousetraps are going to get fissioned or triggered. And so let's look at how that actually looks mechanically with a bunch of mousetraps here. Sorry, there's no soundtrack on this. You'll have to provide your own. So you know what's going to happen. They're going to drop one in, and then we'll view it from that's just one. All right, so that's how it works. So we got 2 coming out. They have set up, now gosh, you think about the amount of work that went into this. There it goes. Nice. I'll stop a second minute. Whoa. Pretty fast. Let's see it in slow-mo. Red one's still going, more of them going. Here, all of the ping pong balls are kind of forced to hit a mousetrap, right, because we have plastic walls there. It's like a very high density of neutrons. So in a surprisingly short amount of time, right, it was just a few seconds, all of those mousetraps are sprung. All the fissionable material gets fissioned. All that energy released explosively, suddenly. Now, by the way, you might not want a bomb if you're a peaceful person. You might want the energy to be released more gradually, in which case you could have some neutron-absorbing rods called moderators to slow this reaction down, keep it below critical, and then you'd have a very nice heat source that could go on literally for thousands and thousands of years. That would be a fission reactor in a nuclear power plant. Incredibly efficient way of generating power compared to something chemical like coal. Another view of this, just nice to see it from different angles. It's super slow-mo. I'll put the link to this, and there's a number of other cool mousetrap movies. This one seemed to be the nicest one I could find. Wow, look at that. Neutron Blizzard. Love that. All in just a few seconds. The end.